We're now going to turn our attention to studying another sort of fundamental question in calculus. So the first question is, how fast is something changing? And that is answered by looking at the derivative. Now what we are going to look at is, how do we calculate the area under a curve? Now, when we talk about area, we know some things from geometry class. We know how to find the area of a circle. We know that the area here is pi r squared. We know that the area of a rectangle is the length times the width of that rectangle. We even know triangles, where we know that if we have a triangle, that in order to find this, we find the base and then we find some height, and then the area is 1/2 base times height. But when we come to looks like this, how would we go ahead and find the area of that? And one of the techniques you might use would be to split this thing up into separate triangles, and then you calculate the triangles and put them together. And it's this idea that we want to sort of keep in mind as we go forward here. So a question that might come up in application or in some sort of math class or out in the real world might be, let's say we've got the area, we've got a curve, f of x, and I want to know the area that is between the curve and the x-axis. How could we go ahead and solve this? Well, we're going to take our motivation from the idea of that we had with this hexagon that I drew and splitting it up into different triangles. Well, not triangles in this case. What we're going to do is actually start off by approximating using rectangles. So if I look at this up here, one thing I could do is sort of like split this in half, and I could draw a couple of rectangles that sort of approximate what is happening here. So if I took the area of these rectangles in blue, it would at least give me a decent approximation for what is happening. And not to say that these are the only rectangles I could use. And I happen to be picking them by splitting this up into sort of nice and then using the function to help me approximate. Maybe I pick these rectangles instead, and I'm getting the heights of these rectangles by using the function here. Maybe I use this, and we would see that actually this is probably a little bit better of an estimate, that the area between the curve that I'm ignoring and these rectangles is a little bit smaller. So it's this idea that we're going to use, is we're going to take our function and we're going to approximate using rectangles with heights given by the function itself. So let's see what I mean by that. So let's say I've got this function f of x equals the square root of x. And let's say I'm going to look between x equals 0 and x equals 4. And I want to come up with what the area is underneath this curve. And so I can sketch a drawing of it. Our technique is to split this up into rectangles and use those rectangles as an approximation. And we use either what we call left endpoints or right endpoints. And so when we say we're using a left endpoint to make our rectangle, it means I'm using, so let's say I split this up into two different intervals. So I've got a length of 2 here and another length of 2. And we always like to split things up so that they're uniform like this. So a left endpoint would be, I take the left side of this interval from 0 to 2, and I draw my rectangle with that as a height. And then for this next interval from 2 to 4, I would take this left endpoint and use that as the height of my rectangle. So the height of my rectangle here would be f of 2, and my height of my rectangle here would be f of 0. Now, we could also use what we'd call a right endpoint. Oh, and we would use notation like L sub 2 for 2 rectangles here. And if we were to do that, we would get that the area that we're suggesting here would be 2 times f of 0 plus 2 times f of 2. And we see that because the length of the width of the rectangle is w is 2, and the height is whatever the function is dictating to me at that point. So if we were to approximate that, we get about 2.828 from there. Now, we can also use what we'd call the right endpoint. So then in this interval from 0 to 2, instead of using f of 0, that left endpoint of the interval, as the height of my rectangle, I could take the right endpoint and use it as my height of my rectangle. So now this would be f of 2 as a height, and then in the next interval, it would have f of 4 as its height. And so here we would use some notation like R2, meaning right endpoints, and we'd have 2 times f of 2 plus 2 times f of 4. And if we were to do that here, we get 6.828 as our approximation. Now, we can see from the picture here that the left endpoints is going to be an underestimate because it's not accounting for any of this area here. And then in this next bit, it's not accounting for any of this area up here. When we look at that for the area under that curve. So L2 is an underestimate, but on the other hand, R2 is actually going to be an overestimate because it's also throwing in all of this area up here. And so really all we could say if we were looking for the area of under the curve A, what we could say is that reasonably we know that A has to be between these two values. Now, we saw it a little bit, at least in the picture up here, that when we used smaller rectangles, it looks as though we are decreasing the amount of error that we have. And so let's see what happens if we do that here. So instead of using rectangles of width 2, what would happen if I use rectangles of width 1 to approximate these things? Well, if that was the case, I would get a picture that would look like this. And so again, the right endpoints are going to be an overestimate because we see that there is this sort of extra area happening in each of these spots here. And we also see that the right endpoints are going to be an or the left endpoints will be an underestimate because of this area missing here. But we can still do the same sort of thing. And we're using the right endpoints, so that means we take the height of our first rectangle at 1, the height of our second rectangle at 2, so that's f of 2. And f of 3 would give us the height of this third rectangle, and f of 4. And since we've split this up into 4 even equal intervals, we might say that R4, as our using our right endpoints, is approximately 6.146. And if we do the same thing for our left hand, then endpoints, we get this. So now we could reasonably claim, based on this, that our approximations for our area A is between 4.146 and 6.146. So you can see that our approximation has gotten a lot better, going from 2 endpoints or 2 rectangles to 4. Now, we could keep going here. We could split this up into 6, 5, or even 8 endpoints. Well, you could do as many as you want. Just a matter of how much you want to do calculations. So for the right endpoints, and I'll just do this as 8 rectangles here. So now, if we're looking at, we split this up into 8 equal intervals here. So this is 0.5, 1.5, 3, 2.5 as these middle points here. But we can still use these rectangles. So we get the height of the rectangle by plugging in the value of the function at that point, and then we get the width by how much we split up the interval. So we had 0 to 4 split up into 8 pieces. So each one of these little intervals right here is just going to be a length of 1/2. So the height of this first rectangle is 1/2 times f of 1/2. And we can go ahead and use this to give us an approximation again. And so when we do that, we get that the right endpoints here will be 6.058 as our approximation. And I didn't draw it in here, but we could do the same thing with the left. And if we use the left endpoints, then really the only thing that's different is we wouldn't have this last rectangle over here, and we would end up with a rectangle using 0 as the endpoint. So that's the real big difference, actually. And so with left endpoints, we get 5.058. And so we can reasonably now assume that our area is somewhere between these two values. And that's really the best we can do at the moment. And you might stop and ask, where is the calculus for this? Well, here's where the calculus comes in. So the area of the graph, the area A of a region S that lies under the graph of a continuous function f is the limit of the sum of the areas of the approximating rectangles. So the idea is you keep chopping this interval up into smaller and smaller pieces using more and more rectangles. And if you take the limit for the number of rectangles that you use as n goes to infinity, and I've got the right endpoints here that I'm using, and I've got this delta x here. I'll explain that in a little while, but that's really just telling you the width because you're cutting the interval up into equal widths. So the f of x1 is sort of the height of your rectangle, and this bit here is your width in each case. If you take the limit as n goes to infinity, then that is going to equal the area underneath that curve. So that's where the calculus comes in, is that we're actually going to be taking a limit as the number of rectangles goes off to infinity, and that tells us what our area is. And not that we have the ways to do this yet, but if you actually do compute this limit, the area underneath the curve here, as the number of rectangles goes to infinity, actually ends up being 16/3, which is equal to 5.3 repeating. So we do know that it is falling in between our approximations here, but it would take us a while. We would need even more endpoints because we're not even right in the first decimal place yet to actually figure out that that is what it is. But we will learn methods for calculating these limits and these areas under the curve in this section and in the next couple.